Welcome back, everyone. Man, in our last module, we wrapped up the capstone, and I gotta say, you did an incredible job. You've got this beautifully engineered, shiny new digital EVM vehicle just sitting there in your driveway. But there's kinda one tiny problem. How exactly do you fuel the thing? I'm your host, and this explainer is brought to you by Forge College. Today, we're popping the hood to look at the absolute lifeblood of the Ethereum network, and that is gas.
All right, let's dive right into this. Here's our road trip itinerary for today's explainer. First, what is gas? Second, the meter versus the money. Third, the road trip model. Fourth, mechanics of consumption. And finally, reading the gas receipt. Let's hit the road.
Section 1. What is gas? The foundational vocabulary. So before we really get going, we've got to establish what gas actually represents. Trying to optimize your smart contracts without knowing this, it's literally like trying to improve your car's mileage without even knowing what a gallon is. Gas is fundamentally an abstract unit. It essentially meters EVM computational work. Think back to that execution trace, right? All those opcodes and stack memory behaviors you studied in the previous module. Well, every single opcode executed, every byte of data processed, every state transition, it all maps directly to a specific gas cost. The network charges this to cap resource usage and basically keep the entire system from just grinding to a halt.
Moving on to section 2, the meter versus the money, measurement versus price. Now this brings us to what's probably the single most absolutely crucial concept for beginners to wrap their heads around. We have got to completely separate the measurement of the work being done from the actual currency used to pay for it. Think of it like this. On one side, we have the meter. These are your gas units, a purely abstract count of the computational effort. Like, say, a simple Ether transfer that requires exactly 21,000 units of effort. The EVM drives this meter strictly based on your code's execution semantics. But then, on the other side, we have the money. This is the Wei, or the Gwei, the actual cryptocurrency you're paying per unit of effort. So while the meter is driven by your code, the price is driven by the open market. The exact same amount of computation can cost wildly different amounts of actual money, depending entirely on network congestion. And here is the simple, elegant little math formula that connects those two things together when it's time to settle up. Your fee paid in Wei equals the gas used, again, that's the abstract meter, multiplied by the gas price in Wei, which is the literal money. Keeping these two variables totally isolated in your mind, it is going to save you massive headaches later when you're trying to figure out if your fee is super high because your code is inefficient, or if the network is just having a really crazy day. Okay, section 3, the road trip model. Gas as fuel. To really make all these transaction fields stick, let's build out a mental model using a road trip metaphor. Imagine you're going on a cross-country drive. The vehicle you're driving, that's your EVM transaction. The absolute maximum size of your fuel tank, basically the maximum gas you're willing to spend, that is your gas limit. The price you agree to pay at the pump, that's your gas price. And as you drive along, the actual fuel you're burning is your gas used. And what about the terrain? Those speed bumps, the steep hills, those are your opcodes and storage operations. Now, if you miscalculate and your gas limit fuel tank runs completely dry mid-trip, the EVM halts, your transaction reverts. You are magically teleported right back home, and here's the real painful kicker, the network still charges you for all the fuel you burned trying to get there. Rough, right? Which brings us to section 4, mechanics of consumption. Why operations cost gas. So, we know how our vehicle works, but let's take a closer look at dissecting the road itself. Why do different operations consume such wildly different amounts of our precious fuel? Well, the network assigns different toll prices for 4 interlocking reasons, all designed to protect the blockchain from resource exhaustion. First, you've got the intrinsic transaction cost. Literally just turning the key in the ignition costs you 21,000 gas. Second is the per-opcode cost. That's the baseline fuel burned for every single computational step. Third is the memory expansion cost. And fourth is the state storage cost. Now let's look a little closer at those last two because, man, that is where the real gas guzzling happens. Memory expansion is super fascinating because it's not purely linear. It actually features quadratic cost growth. Imagine you're driving down the highway, right? And every single time you need more trunk space, you magically hitch another heavy trailer to the back of your car. The more trailers you add, the faster your fuel consumption spikes. So what this means is, if your code triggers large, repeated memory growth, especially if you're doing it inside of loops, your gas costs will absolutely skyrocket way faster than you might think. And then, oh boy, then we have state storage, specifically the STOR opcode. This is without a doubt the heaviest toll booth on the entire Ethereum network. Why? Well, because writing a permanent storage slot to the global state increases the long-term burden on every single node across the entire world. It literally alters the massive Merkle-Patricia trie. So the protocol intentionally makes modifying the global state incredibly expensive, basically to discourage you from just cluttering up the blockchain with unnecessary data.
All right, Section 5, reading the gas receipts, transaction breakdown.
So the crucial point now is knowing how to actually identify these costs in the wild. Let's bring all of this together by looking at a concrete transaction breakdown. Imagine a simple function call that stores a 32-byte value and emits an event. Here is your itemized fuel receipt. We start with that intrinsic base cost of 21,000 gas. Processing the transaction's call data adds another 2,400. The function prologue, moving things around the stack, that costs 3,200. Resizing the memory to copy the event data, 1,500. And then, bam, we hit the massive SST or write, which demands a whopping 20,000 gas. Finally, logging the event data itself costs 3,000. That brings our grand total gas used to 51,100 units. Now, what's really interesting here is how clearly the dominant cost driver stands out. Out of that 51,100 total gas, 20,000 was consumed by just that single state storage right. It is a massive chunk of the total. If you were going to optimize this contract, this breakdown tells you exactly where to look first. Like, if you can redesign your logic to avoid writing that variable to permanent storage, you immediately slash a huge percentage of your transaction's overall cost. It's a real game changer.
Section 6, conclusion and optimization levers, actionable targets. Our goal today was to give you the vocabulary so you can translate those execution traces into actionable, measurable targets. So let's quickly recap the core takeaways. First, always separate the meter, your abstract gas, from the money, your GUE. They're two totally different planes of existence. Second, budget your fuel wisely using gasLimit, and always leave a little headroom so you don't run out mid-trip. Third, watch out for that quadratic trap. Optimize your loops to reduce repeated memory expansion. And finally, above all else, minimize those incredibly heavy state storage rates. Treat the global state as a precious, incredibly expensive resource because, well, it is. But this leaves us with a fascinating and slightly dangerous question for our next lesson. What actually happens in the transaction pool when your gas price and your gas limit collide under the pressure of a highly congested network? Who pays what, and how exactly do validators choose your transaction? We are going to untangle the whole shebang in our next explainer. To dive deeper into this subject and master the rest of your Web3 fundamentals, be sure to visit Forge.college. I've been your host. This explainer was proudly made by Forge College, and I will see you in the next one. Keep building and keep optimizing.